Okay, good afternoon. Let's start with this discussion session. Today we will spend some time, first of all, with this agenda. First of all, we are going to solve these questions in homework 2. So we will solve the questions. Please ask any questions you might have or any comments about the solution. Afterwards, we will go to Lab 2. Let's see if you have questions. You know that you have to submit Lab 2 by Sunday, so it's a good opportunity for you to ask as many questions as you have regarding this lab. And afterwards, if we have time, we will start solving homework 3 that you have submitted last night. So let's start with homework 2. And we will start with question 2 in homework 2.
Okay, so we start with question 2, since question 1 was the review of the papers. I haven't checked it, but probably you are doing that, right? As a part of the homework, you are submitting them to the hot CRP system. Okay. Yeah, just don't forget to submit it over there on that system, rather than writing it in PDF format and submitting it with the homework. So it should be on the hot CRP. Okay, so. Probably you will need first to be reminded of the question. It was part of homework 2, which was a few weeks ago. Probably you forgot the questions that were here. But this question is basically about main memory and its organization. Right? So here at the beginning, it gives you a small piece of code, which is a simple array traversal. It goes through all elements of an 2-dimensional 8x8 array and sums up all elements right here in this line. So here this question uses kind of weird terminology. So it says 8-way interleaved memory. So here it really means banks, as it is clear here in this picture. So it is named as from bank 7 to bank 0. And it is byte addressable memory, which is another important thing that it gives you. The total size of memory is 4 kilobytes. And those elements of the array are 2-dimensional. Each element is 4 bytes in size and stored in memory in column major order. So which means, so in row major order, elements of a row are in consecutive memory addresses, right? So in column order, it's vice versa. Elements in the same column are in contiguous locations in the memory. So basically, this means since this inner loop iterates over the row elements first, you have some accesses that are spread, that have some strides in between, right? So you're not accessing, when traversing this, you're not accessing elements contiguously, right? But you're jumping to different addresses by some stride. Okay, and the width of the memory bus is 32 bits, 4 bytes, and each memory access takes 10 cycles. So those are all information provided in the text, but there's also some information here in this picture that you will need to take into account. Okay, so the first question is, since the address space of the memory is 4 kilobytes, 12 bits are needed to uniquely identify each memory location, each byte, right, because we are addressing bytes here, and specify which bits of the address will be used for what. And here you have some space that you need to fill. So here, byte on the bus. So the bus was 32 bits, right? So it is 4 bytes. To address 4 bytes, you will need 2 bits. right? So where those 2 bits should be in a (12-bit) address. So this is 12 bits. So this is the entire address where those 2 bits should be placed. Right, so if you look at this picture here in the down part, it shows the how data is organized within the chips of the DRAM, right? So this is a picture of a single bank, of bank 0, of rank 0. And here you can see that bytes of elements are spread to different chips. Right, so here, A00's lower bits are in this chip, then the next 8 bits are on next chip, and so on. So that means first thing you interleave in your address are the bytes. Right, so you can infer this from this information by looking where bytes of the elements are placed inside the chips. Okay, so we know that this is like 2 bits, and this should be the first 2 bits of an address. So here what we need to fill is 1 to 0, right? And then the next thing that we need to fill is interleave or bank bits. Again, we look at this picture, and we see that elements inside a row are mapped to the same bank, right? So A00 is here, and A01 is on the next row of a bank. And the elements of columns are in different banks. Right, so we have 8 banks in total. It says 8-way interleaved, so we need 3 bits. Where those 3 bits need to be? So we access in, it is stored in memory in column major order, right? So if it's stored in memory in column major order, then those are supposed to be consecutive bits, right? So the element in the next column, next element in the same column is supposed to be in consecutive memory addresses. That means the first thing that needs to come after the byte address should be the bank address, right? So we know it is 3 bits, and it should come after the byte address. So it will be from 2 to 4. It's the bank address. Is that clear? Because it is kind of tricky to think about, but yeah. So basically, you look here. The next element is here, and this needs to be in consecutive addresses, right? So this needs to be then the bank address, the next thing to come in the 12-bit address bits. Okay, and then chip address. So this is again kind of like odd terminology that I think never used in the class. So here by chip address, it means actually the raw address, right? Address inside the chip. So we can maybe correct this as a raw address. So you know all chips operate in lockstep, right? So you don't have individual access to the chips unless they are in different ranks. Okay, so this is row address, what is meant here. And so we know how many rows we have from this picture, right? So it has put here dots, but we know that if you look here, the elements from 0 to 7 come here. So this means we have 8 rows in total. So again, we need 3 bits to specify the row address. And the row bits needs to be, again, the next thing that comes, basically the bits after 4th bit. And the reason for this is basically, again, how the elements are laid out, right? So, so this is rank 0, right? And all the data, the entire array, A by array, is mapped to rank 0, right? and those are consecutive addresses. So if we switch the rank, if we put rank bits as the next thing, then the data should have been in the next rank. But here in this picture, we see that it's only on the rank 0. So the next thing to come is 0 address. And again, here from the elements, here we see that it's on the next rows. So we write here from 5 to 7, right, 3 bits. And then the rest is rank bits from 8 to 11. And then we can tell also how many ranks we have right after this. And you can also tell it by looking at the size of the memory it is giving us, 4 kilobytes. Okay. Any question about this? Anything that's not clear? Okay, so you have probably checked the solution already, but sometimes the solution is not that clear. So it's good to iterate over it. Okay, the next question, it's on this side. How many cycles are spent accessing memory during the execution of the above code? Compared with the number of memory access it could take if the memory were not interleaved, single 4-byte wide array. So this means if you have just a single bank and you don't have ranks, I suppose. But ranks are not used anyway. Okay, so let's first calculate how many cycles it will take. So each access to the memory is 10 cycles. If you have multiple banks, if you access multiple banks, this means you can overlap some of the latency of the accesses, right? But here in this case, if you look at it, so the elements are accessed in row major order. So data is placed to the RAM, to the memory in column major order, but the accesses are in row major order. So you first access this element, then this element, then this element. So you have conflicts in a bank, right? So you interfere for the same bank, always. Almost always. So if you look at the inner loop, so you access the same bank, you access the bank 0 8 times, and then when switching to the next iteration, so once we finish the inner loop once, and then go to the outer loop, and then get into this again, we switch to the next bank, right? So we have a little bit overlap here when we switch to the other bank. And basically, how many times we have this overlap? It is 8 times, right? Because we actually it's 7 times because we don't have anything to overlap with in the last outer loop iteration. So it is basically we have just to visually represent the pattern we have here. I will use this notation. So C for conflict, right? So we make the first access as C. We don't have anything to overlap with it because it's the first access. So I'm here noting the accesses during the execution of this code here. So when accessing the first element, we go to bank 0, or maybe it's better just to write the bank number. Okay, so we go to bank 0. We go to bank 0 8 times, right? Okay, I'll just write it. So this is 8, and then we switch to bank 1. So here we have some overlap, right? So each of those took 10 cycles to complete, each of those zeros. But here we can overlap. So it's part of this access comes for free, right? So we can overlap it with the previous 10 cycles access. And then we continue to access 1 and then switch to 2. So if you consider this pattern, you will see that those overlaps happen 7 times because in the last iteration, we don't have anything to overlap it, right? So we here somewhere we end with 6, then comes 7, and this is the last thing that we can overlap. Okay, and basically to calculate how many cycles it will require is, and you can also count it since the array the array size is very small. One option is to count it, but you can also formalize it. And here the formula, the easier way of calculating this will be assuming all accesses happen. Okay, I'll just write it here. So we have 8 by 8 accesses, right? We are accessing in total 64 elements, and each of those will take 10 cycles if all of those were bank conflicts. right? So this is actually the other case, a single 4-byte wide array case, right? And you can calculate how many cycles this is. So this is 640 cycles. Okay, but since we have some overlap in latency, we need to subtract this latency, subtract the overlap. So here we have 9 cycles overlap, right? Basically, after issuing a request to bank 0, in the next cycle, we can issue a request to bank 1, where the request to bank 1 will complete 1 cycle after completing the request to bank 0. Right? So we'll have only 1 additional cycle. So we'll need to subtract 7 by 9 from this, right? And the result is basically 640 minus 63. That is 7. Is that correct? Yeah. Cycles. Yeah, so this is the case. The number of cycles this program takes to execute on an 8-bank memory system. If you had only 1 bank, it should have been slightly more. Yeah. Okay. I'm going to the next one. If there are not any questions about this, could you press the button while talking? It's good to have it in the recordings. Yeah. Is it working? I think you need to press it hard. Oh, it's not working? Okay, okay. I mean, it's not convenient. Okay, yeah. Yep. Is it? Yeah. I mean, there are still rows here, right? So the first thing is row, but it indicates the row number, right? So this guy here, this is the row number. So it's also same in the picture, right? So this is the row number. So this is like A10 means the first element of the second row, right? So this is row 0, this is row 1, and this is the element that is referenced here. Yeah. So elements of columns. So, okay, let's read the question again. So it says here that are 4 bytes in length, elements of array A are 4 bytes in length and are stored in memory in column major order. So in row major order, you store elements of rows in consecutive addresses. So it says the elements of columns are stored in consecutive addresses. So this is the information that is given to you. And then we filled those numbers here based on that information. Okay, I think I'm going to the next one. Can change be made to the current interleaving scheme to optimize the number of cycles spent accessing the memory? So here what we did wrong was, by saying wrong, I mean the reason why it took too many cycles was basically because we laid out the array in memory in a way that is not efficient to access, right? So we stored the array in column major order, but we were accessing it in row major order, which caused those conflicts, those bank conflicts. So what we can change in the scheme to solve this problem is basically to replace bank bits and row bits, right? So if we change those, so if we put here so both are 3 bits. So if we do this 7 to 5 and do this 4 to 2, then the problem is solved, right? So by accessing this array, we will first access different banks. We will go to different banks for consecutive elements in row major order. And then and then switch to the next row. Basically, we'll have a lot of parallelism, bank level parallelism. Okay. If yes, which bits of the address is used to specify byte on the bus interleaving and blah, blah, blah. So basically, we already did that. So those byte on bus stay same, rank bits stay same, and we only switch chip address or row address and bank bits. Okay, with the new interleaving scheme, how many cycles are spent accessing the memory? Remember, the elements of array will be still stored in column major order. Okay. So basically, what has changed is now in this pattern, it will be like this, right? So instead of like 8 zeros, here we will interleave between the banks, 1 to 3 to 7, right, and then go to 1. So since we have 8 banks and the latency is 10 cycles, we may not be able to like overlap some of the latency, right? But so let's calculate it to see what happens exactly. So I will draw this like this. So here at this point, this is time 0. We start the first access, and it takes 10 cycles. Right? It completes at time 10. And then on the next cycle, we can start the access to the next element. It will complete in 11. And so basically this continues like this, and the access to the last bank will be started on cycle 7, right? And it will complete on cycle 17. So we will have this this pattern continuously. So here on cycle 7, on cycle 8, we will again want to access bank 0, right? But but at cycle 8, this bank 0 is still busy. It is servicing the previous request. So this will need to wait till this point, right? So basically, each iteration of the inner loop will take 17 cycles. I'm sorry, it will take 10 cycles, right? So it will take this much each iteration, plus in the last iteration, we will need to wait for the last access to complete, which will add another 7 cycles. So basically, it will be 8. We have 8 outer loop iterations by 10 cycles, multiplied by 10 cycles, plus 7 cycles for the completion of the last access in the last iteration. And this is 78 cycles in total. Right. So just by changing the interleaving scheme, we have improved the execution time of this program significantly. Okay, and D is very similar to this, but the difference is that instead of like changing the interleaving scheme, it asks what kind of optimization we can make to the program to achieve better performance. So this is like something that you have probably taken into account, right, when writing your programs. You are trying to access your arrays in row major order because you know that the array that you have allocated is stored in row major order in memory in your system. So you try to write the program, if possible, in that way. So this is, again, like a similar thing. So here, since the array is allocated in column major order in the memory, if you access it in column major order, again, you will achieve the same effect of changing the interleaving scheme. on the addresses. So what we need to change in the code is basically, since it won't change the result, we can replace I with J and J with I, basically swap the iterators here. Right. And then it will be exactly the same as changing the interleaving scheme, and we will achieve the same performance. So here the answer to how many cycles are spent accessing the memory will be the same, 87 cycles again, right? Okay. Any questions about this? Everyone's happy with the solution? Okay. I think that was all for the second question.
Okay, now let's continue with question 3. In question 3, it's about memory scheduling, and we have to calculate what's the stall time for each application for different scheduling policies. As explained in the question, there are 4 different DRAM commands. We have the activate and pre-charge commands that are essentially opening or closing a row, and then we have read and write commands. In the figure, what we have is a snapshot of a particular point in time where we have a certain number of requests to different rows in 2 channels. So each of these requests go to a different row, meaning R3 meaning to the 3rd row, R5 to the 5th row, and so on. And we have 3 different applications running. So we are going to calculate, we're going to see how the different memory scheduling policies affect the different applications. And we will calculate what's the total latency for the different policies. So let's start with section 3.1, where we are going to deal with application unaware memory scheduling policies. So essentially, there are 2 memory scheduling policies considered here. The first one is first come, first serve. And the second one, as you know, is going to exploit row buffer locality. It's FR-FCFS. So let's first take a look at question A in 3.1. It says, using first come, first serve scheduling policy, what's the stall time of each application? So it is first come, first serve. So this means that the memory requests are going to be processed or are going to be scheduled in the order they arrived to the request queue. Observe that in channel 0, row 3 is open. In channel 1, row 12 is open. So this means that the first request that is going to be considered R3 in channel 0 is going to hit. Similarly, request 12 in channel 1 is also going to hit. Because the policy that we are going to use here is first come, first serve, the next request to be scheduled in channel 0 is request 5, so this one is going to miss. We need to close row 3, and then open row 5. Again, the next request is to row 3, so we will have to close row 5 and open row 3. So this is, again, a miss. For R9, also a miss. R12, also a miss. R3, again a miss. And then, because R3 will be open, we have a hit for row 3, and then miss, 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 and miss. So we can, for application A, in the end, the total stall time will be the maximum in the two channels, channel 0 and channel 1. So in channel 1, for application A, you see that this is the last request from application A. So if we count the number of hits and misses here, we see that there are 2 hits plus 1, 2, 3, 4, 5, 6, 7, plus 7 misses. For application B, again, the maximum of the 2 channels. For application C, it's also the maximum of the 2 channels. So we see that the last request from application B is here, is this request to row 17. So essentially it's the same as application 4, application A, plus 1 more miss. And the last of the request is to R21, is from application C. So then it's 2 hits plus 9 misses. So in channel 1, we see that after this hit in row 12, this is a miss, miss, miss. These are all misses. So for the 3 applications, we have 1 hit, which is the first one, the first access, and then a number of misses, depending on when they finish, when they have their last request. This is the last request from application B, the last request from application A, and the last request from application C. They will have 9 misses, 8 misses, or 10 misses. So that's the way we have to proceed in part A. In part B, now we consider first ready, first come, first serve. So again, we will see for the 3 applications, A, B, and C, the maximum in both channels. And we see again that, so we start with this request to row 3, essentially because the row 3 is open. So we are going to choose a request that hits in the row buffer, in the local row buffer. So this is a hit. And because the row is open, we want to schedule all requests that are going to hit in this row. So this is also a hit, 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 and hit. So we can already see that for application A to be completely scheduled, we will have to consider these 5 hits plus some number of misses, in particular miss when accessing row 5, miss when accessing row 9. So this is plus 2 misses. So then, if we consider application B, observe that here, once we have finished with request to row 9, the next request is to row 12. This will entail a miss. Next one is to row 11. This is also a miss. And the last one is to row 17. It's also a miss. So we have 3 more misses. 5H plus 5 misses. And for the last of the applications, for application C, we again see a miss for this request to R21. So we have to add 1 more miss. We can proceed similarly in channel 1. So, sorry. So we have a hit to row 12. Because row 12 is open, we keep it open so that we can hit here and here. These are 3 hits. Then there are no more hits from in row 12, so we have to close row 12 and open row 18. This entails a miss, but observe that we also have 1 pending, 1 outstanding request to row 18, so this is a hit. And finally, to row 19, we again have a miss. So this, for application B, you can see that we have 4 hits plus 2 misses. Next request in the queue is to R3 from application A. So this is a miss. Row 1, again a miss, miss. And the final one is R2. So we are adding 4 more misses for application A to finish. We have to wait for 4 hits plus 6 misses. And finally, for application C, we have a miss in row 27. So finally, we have to wait for application C 4 hits plus 7 misses. So this is if we apply the first ready, first come, first served policy. You see that the problem with this policy is that it doesn't take into account the individual characteristics of the applications. So for example, even though it's efficient from the point of view of row buffer locality, actually that's related to the answer to question C, that it's efficient from that point of view, it might unfairly delay some of the applications. In this case, you see that even though application C has only 1 request in the queue, it has to wait for all the applications to finish. So that's why in the next part, in 3.2, we are going to consider application-aware memory scheduling. The last question in 3.1 says, describe briefly the scheduling policy that would maximize the request throughput at any given bank. This is first ready, first comes, first serve. As you can see, is the memory scheduling policy that we have been considering in this first part. So as I was saying, in the second part, in 3.2, we want some scheduling policy that is aware of the behavior of each application. So in particular, part A proposes a policy called scheduling policy X, where application C is going to be prioritized because of the fact that it's the one with the least number of memory requests, so we don't want to unfairly delay it. So that's why we're going to prioritize application C. So, because application C is prioritary, the first request to be solved in each of the channels is R21 and R27, respectively. And so we will need to close row 3 and close row 12 in channel 1. This entails a miss in row in request 20 for request 21 and a miss for request 27. So for application C, the stall time is going to be the maximum of M and M, because we have 2 misses. Then, let's see what we have to do with application A and with application B. The question says that for 2 applications with the same priority, and A and B have the same priority in this part of the question, we are going again to apply first ready, first come, first serve. So after in channel 0, after serving request 21, we will serve request 3, for application A. This is a miss, and this will hit here, 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 and here. And then, once the requests to row 3 have been completed, we continue with the next request, which is R5. The next request to arrive to the queue is to R5, so this is a miss. Then R9, and this is a miss. So for application A, we have 4 hits plus 4 misses to bank, to channel 0. For application B, after finishing with all the requests from application A, we still have to service this R12, provoking a miss, then R11, a new miss, and R17, a new miss. So that's why for application B in channel 1, we have 4 hits plus 7 misses. And now let's take a look at channel 1. For channel 1, after serving this miss, this access to row 27, we go to row 12. And once row 12 is open, we can hit with this request and hit with this request from application B. Then we go to the next request in queue, a miss for R18, and then we can hit here. And finally, a miss for R19. So in order to serve all the requests from application B, we have to wait 3 hits plus 4 misses. And we will finish with request from application A. This is a miss. All these are misses. So for application A, we have to wait for 3 hits plus 8 misses. Is that clear? Any questions? Okay. So then the last part of question A says, can you design a better, an even better scheduling policy? Well, this is like an open-ended question, so you can answer many different things. You can come up with some strategy that prioritizes, I don't know, for example, because in the beginning of this question A for policy X, we have considered that we want to service application C first because it only has 1 request in each queue. So we could, for example, consider a similar policy for the other 2 and say, okay, we are going to count the number of requests coming from each application, and in order to not unfairly delay them, we are going to prioritize them in the opposite order, that the number of requests that they have. So for example, in channel 1, we would prioritize application B with respect to application A. That's a possible policy, and that's a possible answer for this for the end of question A. Regarding question B, we actually going to assume something like that. I mean, what we propose is assign priorities to the other two applications such that you minimize the average stall time across the applications. So what we can propose here is that C has more priority than B and B more priority than A. So this is a new scheduling policy, and we are going to consider this new scheduling policy for part C. This is policy Y. It says, using our new scheduling policy, what's the stall time of each application? So again, the highest priority is for C. So these two misses are first serve. For application C is the maximum of M and M. And then the priority in both channels is going to be application B. So we first we will serve this row 12, provoking a miss, row 11, and row 17. So for application B in channel 0, we have to wait 4 misses. In channel 1, we have a miss here. Then we can hit these 2 rows. Then again a miss. We can hit here, row 18, and then a miss. So in channel 1, we have to wait for 3 hits and 4 misses. And then let's see what happens for application A. In channel 0, after these 4 misses, we have a miss in row 3. This is a hit, hit, and hit. And also here one hit in row 3. And then a miss. And then a miss to serve row 9. So finally, we have to wait for 4 hits and 7 misses in channel 0. In channel 1, we will have misses for all the remaining requests from application A. So finally, it's 3 hits plus 8 misses. And that's actually all. I mean, the last part, D, says order the 4 scheduling policies in the order of lowest to highest average stall time, as you will have calculated the stall time for every application and every policy. You can calculate the average, and you'll see that this is the order. So that's all regarding this problem 3. Any questions? Okay. Hopefully it's clear. So now let's take a quick look at the next exercise. The next problem is the potpourri about main memory. So as it says a machine has 4 kilobyte DRAM main memory system. Each row is refreshed every 64 milliseconds. And it's important when you solve or when you read this solution, it's important to keep in mind this note. It says this is an open-ended question. So there might be many different ways of answering this question when we grade your answer, we will take that in mind. So we will consider probably any answer that you might give. It's going to be good, or it's going to be interesting. These are just some possible answers. It's important to keep in mind that for these answers in this question, so the answer that you have here in this solution, we are going to consider that this memory, or the memory scheduler, uses first ready, first come, first serve policy. And so the answers that you can read here are given assuming this scheduling policy. So part A says the machine's designer runs two applications A and B on the machine. Although applications A and B have similar number of requests, application A spends surprisingly larger fraction of cycles stalling for memory than application B does. What's the reason? So assuming that we are using a first ready, first come, first serve, a possible answer to this question is that application A has such a large fraction of cycles because there are many row buffer conflicts for application A. Luckily, it's much better for application B, probably many row buffer hits. The second part B says application A also consumes a much larger amount of memory energy than application B does. What might be the reason for this? It's again because of row buffer conflicts, because row buffer conflicts consume more energy because they require pre-charge, activate, and read-write. So if the amount of energy consumed by another application, in this case application A, application A consumes more memory energy. So for example, application B that we are assuming that it has more row buffer hits. This means that we don't need to continuously close and open new rows. So because we are hitting the row, so that's why the consumed energy is less, is lower. Part C says when applications A and B are run together on the machine, application A's performance degrades significantly, while application B's performance don't degrade as much. Why might this happen? So it's important, this is interesting because we have to keep in mind that applications might interfere with each other. So in this case, if we have, as we are assuming, a memory scheduler that favors row buffer hits, like the FR-FCFS scheduling policy, probably this memory scheduler is favoring one of the applications, in this case, application B, because it has many more row buffer hits than application A. So that's the reason why the performance of application A degrades much more. Part D tells us to consider a smarter policy to refresh main memory. And now the idea is that one row is going to be refreshed only if it has not accessed the past 60, it has not been accessed during the past 64 milliseconds. And it says, is that a good idea or not? Well, this can be a good idea because it's obviously going to reduce the amount of energy spent on refresh. Also, this is going to affect the amount of energy that is going to be spent by each application. So if we have a large fraction of rows that have been accessed, well, they won't be refreshed every 64 milliseconds, so we can have we can have an improved refresh outcome. The last part E, says the refresh energy consumption when application B is run drops significantly when this new refresh policy is applied, while the refresh energy when application A is run reduces only slightly. Is it possible? Well, again, this is related to the memory footprint of the application. So, for example, in this case, we can consider that application B has a large working set, while application A has a much smaller working set. So because this working set is much smaller, the number of rows that is going to be accessed is much smaller, so they won't be refreshed every time they are accessed. They are open or closed. So they will still need to be refreshed every 64 milliseconds. So that's more or less the reasoning that we can follow to answer this question. If you don't have any questions about that, then we can go to question number 5. Oh, okay, yeah. Let's have a break, because now it's 1:15. Let's have a 10-minute break, and then we will continue.
Okay, we are solving now the question 5, that is about banking on caches and memory. Well, I'm going to read the question first. So a processor's memory hierarchy consists of a small SRAM L1 cache and a large DRAM main memory, both of which are banked. So the processor has 24-bit physical address space and does not support virtual memory, meaning that all the addresses are physical addresses. An application has just started running on this processor. So the following figure shows the timeline of memory references made by that application and how they are served in the L1 cache or main memory. So we can hear this is the part of the cache access timeline, and this is the memory access timeline. So this is the time. For example, here, when accessing this address, we have a miss, and when we access the next address, we have here a bank conflict. The bank conflicts are represented with this in these areas here, these green areas in this case. So here we have bank conflicts. So, okay, I will continue reading. For example, the first memory reference made by the application, so this one, is to byte address, this address. We assume that all references are byte-sized reads to byte addresses. So, however, the memory reference misses in the L1 cache. So here, assume that the L1 cache is initially empty. So immediately afterwards, the application accesses main memory. So in this case, we miss here and we access main memory. Where it experiences a raw buffer miss, this case here. Initially assume that all banks in main memory each have a row open that will never be accessed by the application. So eventually the cache block, and only that cache block that contains the byte address, this one, is fetched from memory into the cache. So at the end of this access. Subsequent memory references may experience bank conflicts in the L1 cache and or in main memory, if there is a previous reference still being served at a particular bank. Bank conflicts are denoted as hatch shapes in the timeline. So in the case of memory, the bank conflicts are these ones, all these, all these, all these, and all these. So in the table, we have the hexadecimal and binary memory addresses. Okay, so we have some assumptions. So from the above timelines and the table, your job is to answer questions about the processor, cache, and main memory organization. These are the assumptions. In L1 cache, the assumption for the block size is that power of 2 greater than 2, so meaning a minimum of 4. For the associativity, the same, minimum of associativity 4. Total data store size, the same thing. Number of banks, the same, minimum of 4, greater than 2, power of 2. And for the main memory, you assume one channel, one RAM per channel. Banks, the number of banks is a power 2 and greater than 2, so the minimum of banks is 4. Number of rows per bank is 2, greater than 2, so minimum of 4. Minimum. Number of cache blocks per row, power of 2, greater than 2, the same thing, 4. The memory contains the entire working set of the applications and initially all banks have their 0 row open, which is never accessed by the application. So first, in the 5.1, some basic questions. So the A is cache and main memory are subdivided into multiple banks in order to allow parallel accesses. What is an alternative way of allowing parallel accesses? So the answer, as Onur explained in his lectures, is multiporting or duplicating. The question B is a cache that allows multiple cache misses to be outstanding to main memory at the same time is called what? The answer is non-blocking or lookup free. Question number C is, while cache misses are outstanding to main memory, what is the structure that keeps bookkeeping information about the outstanding cache misses? This structure often augments the cache, and the answer is miss status handling registers. The next question is, which is larger, an SRAM cell or a DRAM cell? The answer is the SRAM cell, because it has more transistors, occupies more area. So related with this question, the next one is, what is the number of transistors and capacitors needed to implement each cell, including access transistors? So for a regular SRAM cell is 6 transistors, and for DRAM is 1 transistor and 1 capacitor. So let's switch to the interesting part of the question, that is about cache and memory organization. So, for the following questions, assume that all subsets and indexes come from contiguous address bits. So, what is the L1 cache block size in bytes? So, for calculating the block size, it's enough to know where the offset, how much offset bits we have in for indexing the bytes inside the blocks. So we can divide the addresses in 2 parts. One is the offset, and this is the part where we identify the block itself, and this is within a block. So we can focus on this heat that we have here in the cache. We're talking about the cache, okay? So for heating in a cache block, we have to access to the same cache block, meaning that this part of the address have to be the same. And this offset could be the same or different. So, for example, if looking at this address that corresponds in binary to this, to having a hit, we need to match these bits. That this could be, for example, the bank bits plus the tag plus the index, for example. This could be in other order, but let's consider all these bits that are the bits that identify a block in the cache. So these bits have to be the same. So, for example, we can assume, for example, that these are the bits that identify the block, and all other bits are the offset. We can see clearly that this is not the case, because if this is the case, for example, in the next axis here, we will have a cache hit because we have the same bits here. This and these are the same. So this cannot be the same. So we can take more bits and see that this is the same case with the next address. So this cannot happen because in the next address we have a miss. And if we assume these bits here, we will have a hit, so this is not possible. If we get more bits, we have the same situation. We don't have a hit here, so this is not possible. If we get all these bits to identify the block, and only these bits for the offset, we see that this is coherent with the next axis because it's a miss. These bits are different from these ones. And if we look in all other axes, we have the same bits here. So this could be a hit in this block. In this case, we have different offset. We are accessing to different words inside the block. Yeah. So if we assume one more bit, we wouldn't have a hit here because this bit is 0 and this is 1. So the correct answer is having an offset of 4 bits. And this means that you have a block size of 16 bytes. Yeah, this is the answer for the first question. So the bit position of the block offset is from 0 to 3. So, questions here? So for the next question is how many banks are there in L1 cache? Which bit positions in the 24-bit physical address corresponds to the L1 cache bank index? So having the same figure here, so now we will focus on the bank conflicts, so in these areas here. In these bank conflicts. Okay, let's see the memory address table. So we conclude from the previous question that these bits are for the offset. So we don't care about this. So our goal is find the bits that are mapped to the bank, to the banks. So we can start from the beginning. So we have here a bank conflict. If you have a bank conflict, it means that the bits corresponding to the banks are the same. So possible candidates for the bits corresponding to the banks are the bits that are the same. In this case, we have these, and also you have these two. Okay, these are possible candidates until now. If we see on the next axis here, we don't have bank conflict, so this is not conflicting with the previous one. So if it's not conflicting, means that the bank bits are different. So the bank identifier is different. So if we take these bits, we see that are the same. So this cannot be the bits corresponding to the bank. So we can eliminate these candidates. And we see here that you have a different value. So this will be the bank 1, and this is the bank 0. So this is coherent what we are seeing here. We don't have conflict because the banks are different, and this bank are the same. In the first two, the bank are the same, and in the next, the bank is different. So we just can conclude that these two bits are for the bank. You can conclude this because we previously see that the minimum number of banks is 4. So with 2 bits, we have 4 banks. So we cannot have less than 4 banks. So these are the bits that are indexing the banks. So we have 4 banks. And the bits, bit positions are 4 and 5. Questions? So next question is about also about the banks. How many banks are there in main memory this time? So which bit positions in the 24-bit physical addresses corresponds to the main memory bank index? So we can do the same thing here. So now we are focusing on the memory, and we can observe, we can make some observations from this figure. First, we have row buffer miss. In the next axis, we have a conflict, which means that they are accessing the same bank. The next axis, we have also a conflict, which means that it's accessing the same bank. And in the next, at this time, we have also one conflict, which means that we are accessing to the same bank. So this means that the 4 first addresses are accessing the same bank. So this means, so let's go to the address table. We can discard these bits here because are the offset inside the cache line, the block. So these are not candidates. Then we have between the first 4 addresses, you have the bank bits should be the same. So possible candidates are these bits are the same, and also these bits are the same in these 4 cases. So possible candidates for banks are so far these. So the next axis is this one. We don't have a bank conflict. So this means that this access doesn't conflict with the previous access and with the access before, and even with the access before of this. So this means that the bank address should be different. So we see here that these bits are equal to the previous bits. So we can discard these bits because they are equal, but the bank is different. We don't have a bank conflict. So we only have these candidates, these 3 bits as candidates. So the possible options that we have until now is that these 3 bits here are indexing the bank. But with this information, the bank could be also indexed by only these 2 bits. Only these 2 bits. Because these 2 bits, so this is, in this case, is 2 and this is 3, so it's different. So could be only these 2 bits. These other 2 bits couldn't be because the value is the same than the previous one. So we discard this couple of bits. In the next access, we don't have a bank conflict with the previous access or the access before. We don't have any bank conflict here. So it means we have these 3 candidates. We can see that if we choose only these 2 bits, we will have a conflict with the previous accesses, a bank conflict with the previous access. So we have to discard also this option of being 2 bits. So the only option that we have now is that these 3 bits are the bank indexes. So this, so we have 3 bits for indexing the bank. So the number of banks will be 8 banks. And the bits are from 10 to 12, I think. Yeah. Questions? So the next question is, what kind of interleaving is used to map physical addresses to main memory? So what we have until now is this. You have 4 bits for the offset. We have 1, 2, 3, 4, 5, 6 bits here that we don't know yet. What are these bits for? Then we have 3 bits here for the bank. Then we have the rest of the bits here that are 11 bits here. That we don't know what they are for. So to identify, so we have 2 options. This section identifies the column inside the row or the row itself. So I'm going to use this clean sheet. Right. 4 reads, 6 reads, 3 reads, 11 bits. Bank offset. So now we are going to look at the row buffer hit rate. So, for example, so again, these are the bits for the offset. We know this, and we know also the bank Bs are these ones. Okay. So we can forget about this. And so, if we look at the row buffer hit, so if we have a row buffer hit, it means that we have the same, we are accessing to the same row buffer. So the row buffer should be the same. So if we look, for example, here in the first case, have these bits, and we can see here that these bits are equal, and here are different. So it means that because we are having a row hit here, it means that these bits here are for identifying the row, and these bits here are for indexing the column inside the row. So coming back to the question, what kind of interleaving is used to map addresses to the main memory? So having this into mind, we see that these are raw interleaving. We are using a raw interleaving mapping because here you are indexing the consecutive. So this is the raw identifier per bank. So this means that consecutive rows are in consecutive banks. So it's a raw interleaving. And this index the column, the cache lines inside one row. But this identifies the row. That in this case, consecutive rows are going to different banks. So, questions? So, the next question, to fully support 24-bit physical address space, how many rows must each main memory bank have? Which bit positions in the 24-bit physical address corresponds to the main memory row index? So we already answered this, I think. So the question is, how many rows must each memory bank have to fully support the 24-bit physical address space? So as we saw this, we have 11 bits per bank to identify the row. So the answer is 2,048 rows. And the bit positions are, these ones are from 13 to 23. And the last question for this question 5 is, each cache block within a row is called a column. Well, we already know that. How many columns are there in a single row? Which bit position in the 24-bit physical address corresponds to the main memory column index? So it's the same thing. We have the columns here. We have 6 bits per column, so the answer is 64 columns. And the bit positions are from 4 to 9, these bits here. So this is the question 5. You have many questions? If not, we can go with the next question.
Okay. Let's quickly go through question 6. In this question, we have a magic RAM, which is a non-volatile memory, and it is 2 times slower than an SRAM. And the access latency is similar to DRAM's cell. The dynamic energy of magic RAM is similar to DRAM, and actually the cost of magic RAM is similar to DRAM too. And magic RAM has higher density than DRAM, but magic RAM has an endurance problem. It means that after 2,000 writes to a cell, the magic RAM is weared out. So in the first question, it asks the advantage of magic RAM over the DRAM. So obviously magic RAM does not need refreshes, which means it reduces the power consumption, and also now we have better bus utilization and less bank contention. And also magic RAM provides the non-volatility, which means it brings new opportunities for the programming models. And question B, it asks about the advantage of magic RAM over the SRAM. So magic RAM has higher density and lower cost compared to SRAM. In part C, it asks that does it make sense to add magic RAM anywhere in this memory hierarchy? So the answer is yes. We can use magic RAM as a part of the address space in option 2. When we have when we have L2 cache miss, we can have DRAM access or magic RAM access. So magic RAM actually keeps part of the address space. Or it can be the whole address space in option 1, and DRAM actually is acts as a cache for magic RAM. So this is the 2 possible options for adding magic RAM. For example, we cannot insert magic RAM between L1 and L2 because the access latency of magic RAM is slower compared to SRAM, and it doesn't make any sense to add magic RAM there. So, and what can we do for reducing the overheads or mitigating that endurance problem? So actually, if we use DRAM as a cache for magic RAM, actually DRAM is filtered some write accesses to magic RAM, and it's good. But what we can do more is adding a write buffer between DRAM and magic RAM. It can be used for coalescing or combining writes. And also, we can use some real leveling techniques to try to uniformly distribute the writes to magic RAM cells. It can, we can have good endurance if we uniformly distribute the writes. So we don't write to one cell 2,000 times and to other cells only maybe 1 time. And also, if we use magic RAM as a separate address space, we can have a technique to dynamically detect some pages that are mostly read-only, and then we can allocate those pages to magic RAM, and it's good to have a good endurance for magic RAM. Yes, that's all. Any questions? Okay, let's have a break for 5 minutes, and then we will go through question 7 and 8, and then lab 2. Yeah.
Continue with question 7 in this homework 2. So for question 7, it's about instruction and data caches. The question says, considering the following while loop is executed on a system with a small instruction cache of size 16 byte, And the data cache is fully associative of size 1 kilobyte. Both caches use 16-byte cache blocks. The instruction length is 4 byte, and the initial value of register 1 is 40. The value of register 0 is 0. The first thing to take into account in this exercise, in this question, is that we are going to assume byte addressed memory. So, because the memory is byte addressed, but the instruction length is 4 byte, and also the data elements that we assume that we are going to handle are 4 byte, you have to take into account that subtracting 4 to the address means that we go to the next element, I mean, or to the previous element. So we are sequentially accessing all the elements in array X and in array Y in this question. So the code essentially has a loop, one load instruction, addition, store instruction, store word instruction, subtraction, and branch equal, and an unconditional branch, J. So let's start with part A. It says, compute iCache and dcache miss rates. Considering two possibilities, this is not here, but considering the two possibilities are X is different to Y, so these are two different arrays, or X and Y are the same array. So first thing we're going to do is calculating the iCache miss rate. Observe that in this code we are going to have 10 iterations, right? Because the value of register 1 is 40, and we subtract 4 in each iteration, so we're going to have 10 iterations. In each iteration, you can see that we execute 6 instructions. These 6 instructions are stored in continuously in memory, right? So we assume that the 4 first instructions belong to the same cache line or cache block, and these 2 are in the next cache block. So observe that every time we have an iteration, we are going to miss for this instruction and also miss for this instruction. This means that we have 2 misses out of 6 cache accesses. Okay, so this is 0.33 is our cache miss rate in this case. For the dcache, there are 2 different possibilities, depending, as we said, on they are different arrays. X and Y are different arrays, or X and Y are the same array. So if X and Y are different arrays, if they are different arrays, we are going to have 1 miss every 4 accesses to each of the arrays. So we will have 2 misses every 8 accesses to these 2 arrays. So this gives us 0.25. This is case X is different to Y. And in case X is equal to Y, we are going to hit, so every time we access X, then we will hit on Y. So this is 1/8, only 1 miss out of 8 accesses. So the resulting, this is the resulting dcache miss rate. Question? Could you press the button? No, because the 4 instructions belong to the same cache block. So in each cache block you have one instruction. In each cache block you have 4 instructions. So once you miss, you load one new iCache block into the instruction cache. So you will have the next 3 instructions in the cache. So you miss for this one, and then you load the entire cache block in your iCache, so that then you find this one, and this one. No, it's because this is a loop. I mean, let's assume that this is an infinite loop, okay, even though it's not. The exact calculation is not exactly, is a little bit, or could be a little bit more complex like this. But assuming that this is an infinite loop, in every loop we are going to have 2 misses. We have the miss when we fetch this instruction, and we have a miss when we fetch this instruction. So we have 2 misses every 6 instructions that are executed at fetch. Yeah, so keep in mind that when you have this miss, these 4 instructions, this cache block is replaced by the next cache block that contains this, and these 2 here that we are not going to use. Actually, we will use them in the last iteration. Okay? Any other questions? Okay. Let's continue. So part B says now, once we know the cache miss rates, let's compute the average number of cycles per instruction, the CPI, using a baseline CPI, ideally a CPI, assuming that we have ideal caches, no cache misses, and this baseline CPI is equal to, and the miss latency for both caches is 10 clock cycles. So here we have to calculate the new CPI for the 2 situations that we are considering, x different to y, x equal y. The CPI is, the actual CPI is the baseline CPI plus the extra latency, the extra clock cycles that are due to iCache misses and Dcache misses. So observe that we are going to have an instruction access to memory for every instruction that we need to fetch. So 100%, so we have accesses for all the instructions. And we have misses for 1/3 of these instructions. So this is the iCache miss rate times the latency, 10 cycles, plus the percentage of instructions that can potentially have data cache miss rates. This percentage is 1/3, because you see there are 6 instructions, and 2 of these instructions could potentially have miss rates because they are reads or writes to memory. So this is the, let's call it percentage mem accesses times the Dcache miss rate times the latency. So in summary, this is 2, is the CPI in the baseline, plus 0.33, the instruction cache miss rate, times latency is equal 10 plus the percentage of memory accesses, 0.33, times 0.25 is the Dcache miss rate times 10. In case X and Y are the same, the expression, the resulting expression is more or less the same, except that we need to consider this lower data cache miss rate. That's part B. Maybe you have more questions, just let me know. In part D, it says the compiler could unroll this loop for optimization. Loop unrolling is one possible compiling optimization that actually we have already described a couple of times in class. It says, how would this affect the CPI? So let's assume that this is possible to be enrolled, because maybe it's not. That depends on the compiler. If we know the possible number of the total number of iterations, we could completely unroll the loop. But we are going to assume that's the case. So we no longer have the loop. So now what we are going to have is 4 instructions. LW, the addition, the store, and the, well, actually, not even the, we need, we need to subtract, yes, to change the index. We are accessing the 2 arrays. So we have 4 instructions, and observe that this is going to affect the iCache, the instruction cache miss rate. Now, what we will have is LW add SW sub, and then again LW add SW sub, and so on. So now we will have a miss for this instruction. This will be hit, hit, and hit. And then a miss for this instruction, hit, and so on. So now we're going to have 1 miss every 4 instructions. So new iCache miss rate will be equal to 1/4, 0.25. So how this affects the CPI? Again, we can use the same expression we have here, and the only thing we have to consider is that now the iCache miss rate is not 0.33, it's 0.25. Okay? And the last part, part D, it says how would the previous result change with a 32-byte iCache? Again, we can go through the previous parts. So the resulting iCache miss rate will be different, right? Because now it's the size of the iCache is twice the previous size that we were considering is 32 bytes. So now we can have two instruction cache blocks. So the 6 instructions fit into the instruction cache. So we are going to have, ideally we could have 100% hits, but the truth is that we are going to have 2 misses, right, in the first iteration. So because we have 10 iterations, in the first iteration we have 2 misses. In total we have 60 accesses to the instruction cache. So this results in a very, very low instruction cache miss rate. question? Keep in mind that even though the instruction is the same from the programmer point of view, it's actually a different instruction in memory because the compiler has unrolled the entire loop. Unrolling means that because the loop is going to be executed 10 times, what the compiler does is taking these 4 instructions and then copy these 4 instructions 10 times. So they are actually different instructions, even though they are the same instruction. You know what I mean? So in the layout in memory is going to be something like this. So this is actually, this LW is actually a different instruction than this. So this one misses, these 3 hit, and the next one misses. Any other questions? Okay, thank you. So now Mohammad will solve question 8.
Okay, let's go through question 8. In this question, we have a very good prefetcher. In parts, it's a prefetch block A before it is required with the load instruction. It means that it has a good timeliness. And also, prefetch blocked some blocks should be evicted from the cache to insert block A. But the good thing is that we evict a block that is never to be used, which means that a dead block in the cache. So, and actually, our prefetcher doesn't waste the bus bandwidth for another request. So actually, it's a good prefetcher. For the part B, we have the same situation for prefetching block B. So after executing the program, we see that prefetching block A has a significant influence on the performance, but prefetching block B doesn't have a good performance improvement. So what would be the reason, actually? So we definitely find out that block A is the miss for block A is a very important miss. So actually, if we prefetch block A ahead of time, we will have a significant performance improvement. But mitigating miss for block B is not important. So one possible reason could be the memory parallelism. Maybe we have 2 parallel misses to block B, or other block is, maybe it could be block C. So if we bring block B to the cache and we don't resolve miss for block C, so we will not see much improvement due to mitigating miss block B. So it could be one reason for this. And actually, it can have other reasons. For example, maybe when we have fine-grained multi-threading, maybe we can, for some reason, we can hide the latency of the miss B. So in the baseline, when we have miss B, the processor is not stalled because we have other active threads that could be scheduled for the execution. But for miss A, the processor would be stalled. So if we resolve the miss A, we will have performance improvement. But if we resolve miss B, we will not have performance improvement. These are 2 possible answers to this question. Yeah. Any questions?
Now it's time to ask questions about Lab 2. I don't know if you have any questions about that. Maybe we can answer here. I guess you are still working on it because the deadline is on Sunday. So I don't know. You can also have the chance to talk with us during the office hours, or you can also post your questions in Moodle. Just let us know if you want to solve any questions here, something that is not clear, or otherwise we can start with homework 3. So in homework 3, same as in homework 2, the first question is the critical paper review. You can use Hotcrab to include your reviews, and actually, even if you don't have time to finish them before the deadline, you can still submit in your reviews later. So it's good that you read the paper, so that's why you are allowed to submit the reviews whenever you want to do it and you finish with the paper. So let's start with the remaining questions. Questions 2 and 3 are about GPUs, so let's start discussing them. In this first one, we are going to study, or we are going to analyze the SIND utilization in a GPU program. The SIND utilization, as you know, is the fraction of SIND lanes that are kept busy during the execution of one instruction or a section of code. So essentially the percentage of active threads that we are going to have in our program. You have a code segment there. It's you see that the code is sequential, but actually we consider that this code is going to be mapped onto GPU, the GPU threads. So this for loop won't be explicitly executed, because in the end, the iterations of this loop. You see that this is a data parallel loop, vectorizable loop. The iterations of this loop are going to be distributed among the threads that are going to run on the GPU. The question says that we consider the warp execution, and the size of each warp is 64 threads, because we have 64 SIMD lanes in the GPU. So the first question asks, how many warps does it take to execute this program? And you see the answer here, because we have 1024 iterations. We are going to distribute these iterations among the warps. So we divide the number of iterations between the size by the size of the warp, and this results in 2 to the 4th. This results in 16 warps are needed to execute this instruction. Actually, this assumes that every 64 iterations are going to be executed by a different warp. Okay, we could have some kind of, yesterday I mentioned during the GPU programming lecture, I mentioned that it could be possible to have some thread coarsening. Thread coarsening means that one thread is going to execute more than one iteration. So even though the answer is 16, but we could also use, for example, 8 warps, and each of the warps would execute one iteration of the loop. I mean, not one iteration, 2 blocks of 64 iterations, 128 iterations in the end. But I mean, the most obvious answer is 16, as you've seen. Part B asks about the maximum possible SIMD utilization of this program, and the answer is 100%. What does it mean? It means that all instructions are executed by all the threads in the warp. So starting for, so we have 1, 2, 3, 4, 5, 6 instructions. These 6 instructions are going to be executed by the 64 threads in each warp. It's important to take into account that there are a couple of if statements. So this means that in the actual GPU code we will have branches, and this entails that it might be possible, or predicated instructions, and this entails that it might be possible that we have some divergence within the warp. If we want to have 100% SIMD utilization, this means that the path that all the threads in each warp should follow is exactly the same. And for that condition to be true, this means that they should evaluate these conditions in the same direction. So this brings us to question C. Please describe what needs to be true about array B to reach the maximum possible SIMD utilization asked in part B. And it says, please cover all cases in your answer. Can you read it? Yes. So the correct answer, the most complete answer, considering all possible cases, is that for every 64 consecutive elements, because every 64 consecutive elements are going to be handled by the 64 threads belonging to one warp, every value in these 64 consecutive elements should be 0 or positive or negative. So that in these two instructions, the 64 threads in each warp do exactly the same. Is it clear? Okay. Part D is a little bit more tricky, perhaps. It's because now we have to calculate the minimum possible SIMD utilization. Keep in mind that the minimum possible SIMD utilization won't be 0, because if no threads execute one instruction, then we simply don't consider that instruction. That instruction is not executed. So that doesn't affect the total SIMD utilization. That's why the correct answer is, the reasoning we should follow is, what's the minimum possible SIMD utilization in this program? We will have to consider those instructions where we can potentially have divergence, where we can potentially have less than 100% SIMD utilization, and try to have the lowest SIMD utilization for those instructions. If you, again, look at the code, you will see that the first instruction will always have 100% utilization. There are no branches there, no predicated execution there, so all the 64 threads in each warp are going to execute that instruction. But then we have two if statements, and the idea here is that all the instructions that are within the if statements are only executed by the minimum number of threads in each warp, and the minimum number of threads in each warp is 1. So what should we do to have only one thread in each warp executing each of the instructions, each of the remaining instructions? So we will consider, you can see the answer here, we will consider that the first instruction, this first instruction that is A equal B times B, the first instruction is executed by 64 threads in each warp. The second instruction is also executed by 64 threads in each warp, because the second instruction is this if, and the 64 threads in the warp are going to evaluate the ETH. So the divergence will potentially start in the next instruction, will start later. And for the remaining 4 instructions, we will have only 1 thread times 4 instructions. This is the actual number of threads that execute the 6 instructions that we have in our code out of 64 times 6. This is the total number of threads that could potentially execute all instructions in our code. And this gives us 132 divided by 384. Is that clear? Okay. Part E asks about the pattern that we need to have this, right? So what pattern what do we need to have every 64 consecutive elements so that only one of these, only one of the assigned threads executes these 4 instructions where we could have divergence. And the answer is that 1 out of 64 consecutive elements must be negative. The rest must be 0. So we can, you can check with the code that that's the correct answer, or the correct condition that should happen for this code. Any questions? Okay. Let's continue with the next problem. Is question 3. And the title of the question is Array of a Structure versus a Structure of Array on GPU. This is something that we talked about when we were the first GPU programming session that we have. Essentially, this will give us an idea of how the GPU memory access works and what we should have to keep in mind if we want to have the most optimized, the most efficient memory access to the global memory of the GPU. So the question says, the next figure shows the execution time for processing an array of data structures on our GPU. Abscissa represent the number of members in a data structure. Consecutive GPU threads read consecutive structures and compute the sum reduction of their members. The result is stored in the first member of the structure. In the graph, you can see the average access time per float. So it's access time, so lower is better. And we see 2 possible layouts, array of a structure and discrete arrays that essentially are the same as a structure of array, because in both cases we consider that all the elements that occupy the same position in the structure are the same member in the structure, are going to be stored continuously in contiguous positions in memory. So when we have threads belonging to the same warp reading these elements, they are going to read consecutive memory locations. And this is going to give us coalesced memory accesses that are more efficient. So the question continues saying, the green line is the time for a kernel that accesses an array that is stored as discrete subarrays. That is, all ETH members of all array elements are stored in the ETH subarray in consecutive memory locations. The red line is the kernel time with an array that contains members of the same structure in consecutive memory locations. First question, why does the red line increase linearly and why not the green line. So the answer says that the GPU global memory accesses are carried out on a per warp basis. All threads in the same warp access the same cache line or memory segment, and then the efficiency will be maximized. That's the case of the green line. In the other case, in the case of the array of a structure, consecutive threads are going to access elements that have certain stride between them. There is a stride. So this increases the number of memory transactions that are going to be needed by a single warp. We will have in the case of the green line, we have one single memory transaction per warp because they always access consecutive elements. In the other case, we always have strides, and the stride is the number of elements in the structure. The second question says, how can the effect on the red line be alleviated? And the answer is the use of caches that could store the structure members that have been accessed. So you access the first, or one thread accesses the first structure member. This produces one cache miss. The entire cache block is brought to the cache, and then for the subsequent accesses, we will find the subsequent members of the structure in the cache. So we will have subsequent hits, and that can improve the throughput of the in the case of the array of a structure. And the last part, the last question, asks about the performance of both kernels on a single core CPU with one level of cache and on a dual core CPU with individual caches or with a shared cache. So usually because CPUs have large caches, they benefit from array of a structure layout. As the answer says, structure members are cached when the first member is accessed. And in this case, we might have more similar performance for the array of a structure layout and for the discrete array layout because usually we have large caches, and it's very likely that we will have the subsequent accesses. We will have cache hits for the subsequent accesses to the members of the structure. On the dual core CPU, in case they have individual caches, in this layout, in the DA layout, we will have cache conflicts, or we might have cache conflicts, because each of the cores has its own cache. They are getting the cache lines from the memory. These cache lines are stored in the individual cache, and at some point they might need to be written, and this might produce conflicts that will be solved by the coherence protocol, whatever it is. We will talk, that we will talk about coherence protocols in this course later, but that's already a concept that you know, and so that's why you can simply answer this question. That problem won't exist in a system containing a shared cache, because in that case, even though they are rewriting, assuming that they might write on the same addresses, they will hit because the cache line is already in the shared cache. So in that case, it will be more likely that the array of a structure and the discrete array layout have the same performance. Any questions? Okay, so then we're done with question 3. I think we have time for one more. Should we? Question 4.
So this is an easy one, so I think. So it's about CMD processing. So suppose we want to design a CMD engine that can support a vector length of 16. We have two options, a traditional vector processor and a traditional array processor. Which one is more costly in terms of chip area? So the answer is this, the traditional array processors. And the reason is because an array processor requires 16 functional units for operations, whereas a vector processor requires only one. So that's the reason. So assuming the latency of an additional assuming the latency of an addition operation is 5 cycles in both processors, how long will vector add instructions take in each of the processors? Assume that the other can be fully pipelining, and it's the same for both processors. So in the case we have a vector length of 1, in both the traditional vector processors and in the array processor, the number of cycles is 5 because we only have one add operation with a vector length of 1. We have we have in one case 16 functional units, in another case 1 functional unit that is enough to serve this in 5 cycles. So what happened with length of 4? So in the array processors, we have 16 functional units, so we can execute all of them at the same time, so we spend only 5 cycles in the array processor. And in the vector processor, we have only 1 functional unit, but we can pipeline. So the first one takes 5 cycles. The next one can be served 1 cycle before, after the first one. So we have 1 extra cycle here, 1 extra cycle here, 1 extra cycle here. So here is 1 cycle in total, 5 plus 3, 8 cycles. So with the vector length of 16, so with the array processor, again, we take 5 cycles because we have 16 functional units. And in a vector processor, it's the same thing. We have to pipeline. So we have the first one is 5 cycles, and the other 15 take 1 additional cycle each one. So the total cycles will be 5 plus 15 multiplied by 1 cycle, takes 20 cycles. This is one question here, some question.